Thank you to Shopify for sponsoring this video. Are you smarter than an ancient Egyptian student? Well, let's take a look at this ancient mathematical document from 1650 BC to find out. This book contains the Rhind mathematical papyrus, though not the original that lives in the British Museum and is over 3,500 years old. This is a 1927 edition by Arnold Chase that contains photographs, translations, and mathematical commentary, so we can actually try to read it. The Rhind papyrus is named after Henry Rhind, who purchased it after it was discovered in 1858 near Luxor, Egypt. The material it's written on is made from the papyrus plant. It's over 5 meters long and about 32 centimeters wide, and it's basically a long scroll of mathematical problems. It was written by a scribe called Ahmes, or Ahmose, who says that he copied it from an even older text, so when this was written down, the maths inside was already old. In his title page, he says that it is an accurate reckoning, the entrance into the knowledge of all existing things and all obscure secrets, which is a pretty dramatic way to introduce a maths worksheet. This is not exactly an exam paper, it's more of a scribe's training manual with worked problems about grain, bread, pyramids, cats, mice, some tricky fractions, and even hints at deeper mathematical thinking. And if you were learning this stuff, you probably weren't just learning maths for fun. Scribes were the people who kept records, calculated trades, copied documents, and were essential for many aspects of ancient Egyptian life. In a society where most people could not read or write, scribal training was a huge privilege and responsibility. So let's take a look at some of the problems to see if we could have survived being trained as a scribe in ancient Egypt, sitting somewhere along the Nile, copying problems by hand, while our teacher expects us to treat fractions as the doorway to all obscure secrets. The first few questions are about dividing bread. Problem 4 asks, divide 7 loaves among 10 men. The answer is written as each man receives 2/3 and 1/30. For us, we might just call that 0.7. The ancient Egyptians didn't have our place value system. This means 2/3 plus 1/30. They actually have a table on the preceding page for numbers divided by 10, as this was a common thing to do. You'll notice that 2/3 is the largest fraction they ever use, and the other parts are always written as 1 over something. They will decompose other fractions until they are in that form, what we call unit fractions. This papyrus actually starts with a larger table showing 2 divided into odd numbers up to 101, converting them into unit fractions. This is that previous question about dividing bread on the actual papyrus. I initially thought, oh, they must have written their problems in hieroglyphics, but actually our scribe Ahmes has written this papyrus in something called hieratic, a faster cursive writing system used by scribes. Here, Chase is giving a transcription first into hieroglyphics. Like this backwards-looking 3 here is actually representing this hieroglyphic for the owl, which represents a certain sound, represented here as M. That's the second surprise. Hieroglyphics, at least when used in this papyrus, are actually phonetic. There isn't a picture for each word, but rather unrelated pictures come together to build the sounds. Rewriting the Egyptian sounds using our alphabet is called transliteration. The Egyptian script is also read from right to left. And on the opposite page is the translation, turning its meaning into English. I'm really amazed that people have been able to decipher this at all. Arnold Chase worked on translating this papyrus over the course of 15 years in his spare time. He first became interested in ancient Egypt in 1910 after taking a trip to Egypt with his wife. He specifically said he wanted this translation to be accessible to mathematicians and the general public, not just Egyptologists. Because he didn't have a background in Egyptology, he had done a chemistry degree before going on to be a businessman and working in his family's cotton mill business. Later in life, he developed an interest in mathematics, and in particular quaternions and 4-dimensional geometry. Let's go to the geometry section and take a look at another problem. This one asks, find the volume of a cylindrical granary of diameter 9 and height 10. This circle drawn around the 9 in the top line indicates that 9 is the circular cross-section, not the height. A granary is a container for grain. The method followed in this solution is a bit like a volume formula where there's subtracting 1/9 of the diameter from the diameter itself, then squaring that and multiplying it by the height. The way I would do this is by saying that volume is equal to pi r squared times the height. So comparing that to their formula, we can see that this term, which is 64/81 times d squared, is how they would find the area of the circular face of the granary. Comparing these two methods further, we can see that their value of pi is essentially 256/81, which equals 3.1605. And that's actually not too far off our value of pi. Their volume comes out to 640 cubed cubits. A cubit is an ancient length unit roughly based on the length from your elbow to your fingertips. And a cubed cubit is what you get if you build a cube 1 cubit wide, 1 cubit deep, and 1 cubit tall. It's the volume of that space. Crazy that we still have a unit that sounds the same, cubit, but with a wildly different meaning now for quantum mechanics. They then convert this number to hecart, which are grain storage units. They don't just care about its physical volume, but how much grain it can actually hold. In some problems, horus I fractions are mentioned. These are sacred unit fractions, which the ancient Egyptians associated with the 6 parts of the eye of the god Horus. They are 1/2, 1/4, 1/8, 1/16, 1/32, and 1/64. These were just special notation used to represent the fractions of hecart or grain storage. These fractions were used a lot because of the way ancient Egyptians would actually solve multiplication or division problems. They would repeatedly double or halve quantities, and each of these fractions is half of the previous one. The Met Museum has a statue of a scribe named Nekare, and his title is Employee of the Granary. He's sitting with a papyrus unrolled on his lap, probably looking at a problem similar to the ones we just read. The museum also has a model of a granary from a similar time that is truly amazing. It was discovered in a hidden chamber at the side of a passage leading into a tomb. The model has 2 sections, the granary proper, where the grain was stored, and an accounting area. There are 6 people carrying sacks of grain, but they are actually outnumbered by 9 people taking care of measuring and accounting, showing how important that job was. 2 scribes are using papyrus scrolls, and 2 are writing on wooden writing boards. These questions here are about pyramids. Problem 56 asks, if a pyramid is 250 cubits high, and the side of its base 360 cubits long, what is its seked? A seked is the ancient Egyptian way of describing the slope or steepness of a pyramid. But to them it wasn't a ratio or an angle, instead it was so many palms per cubit. A palm is another unit of measurement similar to the size of a hand. In fact, it says here a cubit is 7 palms. We often think of a slope as rise over run, but to find the answer here, you'll actually want to find the run over the rise. The run is half the base width. Divide that by the rise, and you'll get an answer of 5 palms and 1/25 per cubit. What it means is that for every cubit upward, the pyramid face moves sideways by 5 and 1/25 palms. Another one of their units is a finger, but a finger is 1/4 of a palm, so this is not quite 5 palms and 1 finger. Experts who have looked at these pyramid problems claim that this concept of the seked suggests early beginnings of trigonometry. These questions about the pyramids aren't trying to teach the scribes how to build them or with any expectation they'd be involved in that process, but instead it seems like they're just using a familiar object to practice geometry, much like how modern math books might use examples like swimming pools or tall buildings and bridges as a way to anchor our thinking. Scribal training seems to have been attached to elite institutions, palaces, temples, and government offices. The British Museum says scribes were among the few literate people in ancient Egypt, which was possibly around 1% of the population. Scribal teachers were likely experienced scribes, officials, or priests. Scribal students sometimes used writing boards that could be wiped or scraped clean and reused as a way to practice handwriting. This is a writing board from around 1980 BC, held at the Met Museum. The description says, the scribe's many spelling mistakes have been corrected in red ink by the teacher. So teachers have been marking student work in red ink for nearly 4,000 years. Problems 69 to 78 are known as PEFSU problems. PEFSU is basically a production ratio for food or drink. Chase says it comes from a verb meaning to cook and means something like a cooking ratio, the number of finished units you can make from one unit of raw material. For bread, it means how many loaves can be made from 1 hekat of grain. A lower PEFSU means richer or more valuable food because each loaf contains more grain. For beer, it's similar. How many jugs or measures of beer can be made from 1 hekat of ingredient? Take a look at problem 71. From 1 des measure, or jug of beer, 1/4 has been poured off, and then the measure has been filled up with water. What is the PEFSU of the diluted beer? Or problem 78. Which is an example of exchanging bread for beer. Suppose it is said to thee, 100 loaves of PEFSU 10 are to be exchanged for a quantity of beer of PEFSU 2. How many des, or jugs, of beer will there be? These problems are interesting because they show that trade took into consideration the quantity or quality of each product, and also that there must have been some kind of standardized production process where people could make food reliably of the same concentration or PEFSU without a lot of accidents and waste. So essentially that they had some kind of organized production line, or at least a system. In ancient Egypt, if you were selling bread or beer, that meant doing business face-to-face, keeping track of goods physically, and relying on scribes to make the whole system work. Today, being a merchant looks a bit different. You might still be making something physical, like a book, a print, a shirt, or a loaf of bread, but the storefront can be online. And that brings me to today's sponsor, Shopify. Shopify is a commerce platform that gives you the tools to start, run, and grow a business, whether you're selling online, in person, or both. I use Shopify for my own store where I sell books directly to readers. It lets me set up product pages, take payments, manage orders, and keep track of everything without needing to do complex calculations or build a store from scratch. That means I can focus more time on making the thing itself, whether that's writing, editing, or making videos. For me, a really important Shopify feature has been the integration with Google and YouTube. This allows me to link my book products in my videos and even have them show up in the little shopping shelf under the video description. YouTube is my main form of marketing for my books, so being able to see the analytics from that traffic source is really useful. I am currently taking pre-orders for my upcoming book Alpha Creek, and Shopify helps me keep track of how many sales there have been, so I know how many copies to print for this release. So if you've got something that you would like to sell, whether it's a physical product or a digital one, you can try Shopify at shopify.com/Tibees. Now back to the Rind Papyrus to look at a very peculiar problem. In problem 79, we are told there are 7 houses, 49 cats, 343 mice, 2,401 ears of grain, and 16,807 hekats of grain. And we're asked to find the total. Each of these terms is related by the multiplier 7. It's 7, 7 squared, 7 cubed, 7 to the power of 4, and 7 to the power of 5. It's implying this situation in which there are 7 houses, each containing 7 cats, which all eat 7 mice, each of which would have eaten 7 ears of grain, each of which would have produced 7 measures of grain. The question is weird because in real life you wouldn't add houses and cats and mice and grain as if they were the same kind of thing, but we have to treat this problem as more of a numerical or geometric progression problem than a realistic accounting problem. It's asking how many total things are involved in the whole chain. and the answer is 19,607. Here there is a note that this is similar to the St. Ives nursery rhyme. But it's also similar to a problem from Fibonacci's Liber Abaci, which came thousands of years later and which I recently covered in a video for its influence on medieval mathematics and an introduction of the Hindu-Arabic numeral system. I honestly didn't expect the Liber Abaci to be popping up in relevance with this ancient Egyptian stuff too. Fibonacci's problem was 7 old women going to Rome. 7 old women go to Rome, each has 7 mules, and on each mule are 7 sacks, and in each sack are 7 loaves, and each loaf has 7 knives, and each knife has 7 sheaths. Find the sum of all the aforesaid. Could Fibonacci have read the Rhind papyrus? It was lost until it was rediscovered in 1858, and so Fibonacci almost certainly had not read the Rhind papyrus itself, and it seems like it was unknown to medieval Europe. Fibonacci's Liber Abaci was written in 1202, and that's 600 years before the rediscovery of the Rhind papyrus. It's more likely that this powers of 7 riddle traveled through mathematical teaching traditions or was reinvented because it's a natural puzzle format. Fibonacci did write about what we now call Egyptian fractions. What I said earlier about them avoiding fractions like 3/5 or 7/10. They always preferred to write things in unit fractions, such as 1/2 plus 1/10, or 1/3 plus 1/15, that sort of thing. Fibonacci wrote about decomposing fractions into unit fractions, just like we've seen throughout this papyrus. But that doesn't mean he knew about the Rhind papyrus, or that his methods came from Egypt. Those fraction methods might have just survived through Greek, Arabic, and medieval mathematical traditions. The Rhind papyrus is not the only maths document from ancient Egypt either, but most were only rediscovered in recent times. Fibonacci likely inherited those methods as part of the arithmetic culture of his time. From problem 82 on, these questions are about finding how much food is needed to fatten animals, such as geese. And it shows how much care a farmer could really put into this calculation, something that I also found surprisingly sophisticated. After this point in the papyrus, there are so many mistakes and missing information that it becomes unintelligible. There are lots of mistakes throughout this copying, but not all would be the fault of Ahmes. Maybe some are from his copying, but some might have been in the original document too. Others might be the result of damage to the papyrus, because there are some missing pieces. Ahmes's legacy as a scribe has been remembered because his documents survived, while the original he was copying seems to have been lost, and that might just be down to chance. Papyrus is fragile. In a damp climate, most papyrus would rot. Egypt's dry conditions made survival possible, but only for documents that happened to end up in the right places, such as tombs or desert rubbish heaps or sealed ruins and dry buildings. This papyrus was found in the ruins of a small building near the Ramesseum. So I guess the lesson is that your homework could, by chance, survive thousands of years into the future and be the thing that future civilizations look back on to try and deduce information about your whole society. There is a note on the back of this papyrus which might have been the scribe trying his pen. It's titled Problem 85 and includes a few random words like kill vermin, mice, fresh weeds, numerous spiders, pray the god Re for warmth, wind, and high water. Another Egyptologist named Gunn thinks it's a cryptic sentence meaning something like, interpret this strange matter, which the scribe wrote according to what he knew. The Rhind papyrus shows the kind of mathematics that a scribe needed to master for their jobs, but Chase's book and his interpretations make it seem like the ancient Egyptians weren't just interested in practical problems. This book is not a practical guide for merchants or farmers to use, even though trade and farming are used as examples in here. Chase says that the ancient Egyptians studied mathematics for their own sakes. The conditions and numbers involved in the problems are more theoretical. There were problems about dividing bread into arithmetical progression or other interesting patterns that are unlikely to occur in daily life. And he says this is an example of pure science in its first beginnings. The 2/n table at the start uses techniques to decompose the fractions that actually look more like number theory than arithmetic. The Rind Papyrus was written over 1,000 years before Euclid, so their math class contained no mention of Euclid's elements, or some of those core postulates of Greek mathematics. This papyrus is from a similar time to the Babylonian tablets, or a bit later, but it looks very different, and it doesn't share the base 60 of the Babylonians. Ancient Egyptian math was base 10, just without place value. So, do I think I could survive an ancient Egyptian math class? Well, women were largely excluded from scribal training, so I might not have been allowed in, and I don't know about my chances of surviving long in ancient Egypt itself, but being a scribe might have been one of the best jobs that there were. One early piece of Egyptian literature is known as Satire of the Trades. It seems to have been used as a school text, and it exaggerates how miserable other jobs are in order to make scribal life seem obviously superior. In it, a father is giving advice to his son, and he lays out the horrors of physical labor. He says the farmer suffers, the soldier suffers, the craftsman suffers, but the scribe gets to sit with the records and command the system. A fairer question might be, can a modern person, with our notation and our calculators taken away from us, learn to think like a scribe? And I think the answer is maybe, but only because people like Ahmes left us notes, and some of those notes happened to survive. Thanks to my Patreon supporters for making these videos possible, and a special shout out to today's Patreon cat of the day, Tilt.